Hello everyone and welcome to this new video. In this fourth video that will be part of the series about absolute algebra, we will look at some more examples of the structure of a group as promised in the last video. In particular, we will start by looking at the additive group of integers mod n. So the first example that we will give in this video is the following. So first of all, maybe some of the viewers might not be familiar with the concept of congruence modulo n, but still let's just give a quick recap. Just to make the video as reachable as possible. We recall that we say that two integers a, b, so two members of the integers, are congruent mod n if n divides their difference, so a minus b. So in other words, if you can find an integer nx such that n times x is equal to a minus b. So this congruence mod n actually has quite a lot of nice properties. In particular, the first one of them is that congruence modulo n is an equivalence relation. So in other words, it is reflexive. So for all integers a is congruent modulo n to itself. It is transitive. So if we have that a is congruent to b mod n and b is congruent to c mod n, then a is congruent to c mod n. And the third one is that it is symmetric. So in other words, if we have a congruent b mod n, then b will be congruent to a mod n. And from the definition, which is this one, all these properties are rather easy to prove. However, in this video we won't prove them. Another good properties that congruence modulo n possess is that of how well operations behave under it. So in particular, we will have that if a is congruent to b mod n and c is congruent to d mod n, then we will have that a plus c will be congruent to b plus d mod n, and a times c will be congruent to b times d mod n. And this will actually justify a definition of addition and multiplication modulo n that actually makes sense. So now we can talk about adding numbers modulo n. So as a quick example of a congruence modulo n, usually one of the main examples that is provided to help people understand modular arithmetic is that of a clock. So we have a clock that after we reach both in hours and minutes, for example 60 minutes, we start then counting, we start counting again from 0. And so let's provide some numeric examples though. For example, we can say that 5 is congruent to 2 mod 3. So why is that? Because, well, 3 divides 5 minus 2. Or maybe 16 is congruent to 6 mod 10. So why is that? Because 10 divides 16 minus 6, which is 10. And these are two simple examples that should give the viewer an idea of what should give the viewer a little bit of an idea of what modular arithmetic is, and should help him pretty much get accustomed to working with it. So now that we have an idea of what congruence modulo n is, let's define the following group. So first of all, let's start by defining the defining the following set, which is we will use the following notation Zn. And it will be the set given by all the following integers. So 0, 1, 2, ... up to n minus 1. So we can think of this set actually also as equivalence classes of integers under congruence modulo n. But we will denote it like this. It's really the same. Now what we want to show is that this set under addition modulo n that we will denote like this is a group. So let's prove it. So we start with the associativity. And associativity follows pretty quickly from the associativity of regular integers. So in fact, we know that for integers a, b, c, then a plus b plus c first, and then a plus b first plus c, these two are equal. So now to prove this for the elements of Zn, first of all, to make a little bit of a distinction, let's use this notation to indicate that we're working with equivalence classes and not so we will use square brackets a, square brackets b, square brackets c that are elements of Zn. So let's consider a plus brackets a b plus c. So where here the plus, actually let's put a n to indicate that it is addition modulo n. So by the definition actually of addition modulo n, we saw that follow that property of the property that b plus c. So if a is congruent to c and b is congruent to d, a plus b is congruent to c plus d. So for this reason, we have that the equivalence class of a plus this is equal to the equivalence class of a plus the equivalence class of b plus c, where here plus is the regular addition. And now, using again the properties of addition modulo n, we will see that this is equal to a plus b plus c, where here this is an equivalence class. And now, by using the properties of addition of integers, we will see that this is equal to the equivalence class of a plus b plus c, and this is equal to a plus b plus addition modulo n of the equivalence class of c. But now, unfolding all of this, we get that this is equal to a plus addition modulo n b, all in brackets, plus the equivalence class of c. And this proves associativity. So associativity is satisfied. So now for the identity element is 0, that is in the set by the way we define it. So 0 is the identity. For the inverse element, so there is an inverse element for each a in Zn, and that element is in particular n minus a. So for example, if we have 0, the inverse is 0. For 1, the inverse is n minus 1. For 2, the inverse is n minus 2, and so on. So we have an inverse, and lastly, so this actually proves that Zn is a group. So from this follows that Zn is a group. But Zn is not just a group, it is actually an abelian group. So let's prove that it's also commutative. Actually, I'll just argue quickly why that is the case. Roughly, it follows in the same way in the way we proved associativity. So for the same considerations, we also know that addition modulo n will be commutative, and from this it follows that Zn under addition modulo n is an abelian group. An abelian group of finite order. In particular, the order of Zn is n, so the number of elements is n. So we have proved what we wanted to show. So now we're ready to move to the next example, and that is we will use as the next example the group that we will call UN. So but what is UN as a set? So UN as a set is just the collection of elements of Zn such that the GCD of n with k is 1. So all relative primes, actually we can also think of these elements as just all the positive integers less than n that are relatively prime with respect to n. So let us give an example of such group. So for example, we can consider the group U6. So what are the elements that are relatively prime to U6? Well, of course 1, because the GCD of 1 and 6 is 1. Well, is 2 relatively prime with respect to 6? No, because 2 divides 6, so that is not the case. Same thing with 3. Is 4 relatively prime? No. Is 5 relatively prime? Yes. So we'll have that the U6 will be just comprised of 1 and 5, and in particular the order of this of U6 will be 2. Now, if the viewer has familiarity with number theory, I want to shed light on the fact that the order of this group in particular is given by the famous function that you have surely worked a lot with in a number theory course, and that is the Euler-Theutian function, which is often represented as phi of n. And so this is in general the order of the group, just by the definition of phi of n, which is just the number of positive integers less than n that are relatively prime with respect to n. So this is exactly the order of this u of n. Now what we want to show is that this group, this set together with multiplication mod n forms a group. So And in order to prove this, we will follow the same steps as before. This time, however, we will have to be a little bit more careful with some of the axioms of group structure. So this time we start by closure, which we will have to be a little bit more careful about, because here we're working, of course, with relatively prime integers, and it is not obvious why it would be the case that multiplying them would give back another member of the same set. So let's prove that this set is actually closed with respect to this operation. And how can we do this? Well, we start by taking two elements, a, b in U of n. And well, we can have two cases. So considering them not now as equivalence classes, but rather as plain integers. So we can have that their product can be either less than n, or it can be greater than n. Notice that since they are relatively prime with respect to n, their product cannot be equal to n for obvious reasons. So let us consider each case separately. So for the first one, for a, b less than n, we will have that then we already have one requirement of the two requirements that are necessary in order to be a member of U of n. The last one is that it should be relatively prime with respect to n. But now we will use a standard fact from number theory, and that is that if GCD of n and GCD of bn are both equal to 1, then their product, so GCD of ab with respect to n, is 1. And let's prove it very quickly. So this by Bezout's identity, we will have that a times x plus n times y is equal to 1. So we have there are some integers x and y such that this is true. And for the second GCD, we will have that again. We will have two integers x prime, y prime, such that bx prime plus ny prime is equal to 1. So now multiplying these, so we'll have that ax plus ny times bx prime plus ny prime. This is still equal to 1. By foiling this product over, we'll have that ax, ab x prime plus an x y prime plus b times n times x prime times y plus n squared y prime, and all of this is equal to 1. And sorry if some of the letters are unintelligible, but okay, now it's bad. So now what we do is we notice that all of this is a multiple of n, so we can write all of this as n times ax y prime plus bx prime y plus ny y prime. We call all of this y tilde. And this similarly is a multiple of AB, and we call this thing here x tilde. So what we got is that AB times x tilde plus n times y tilde is equal to 1. And by Bezout's identity, this implies that the GCD of AB with n is 1. So we quickly verify this identity. So by this, we have that if AB is less than n, then by this consideration here, it is also relatively prime with respect to n. So we have that AB is in in U of n. So nice. So now for the other case, a times b is greater than n. First of all, we will satisfy one of the two requirements in order to get inside U of n, and that is, let's restrict to the positive integers less than n. How can we do that? We can do that by subtracting to a multiple of n, and then we can call L times n times L, where L is a natural number. So this will be less than n. And now that we have this, which is one of the two requirements satisfied, we want to prove that the GCD of AB minus Ln with n is 1. So we already know that the GCD of AB with n is 1. So by Bezout's identity, we know that there are x and y in the integer such that AB times x plus ny is equal to 1. So in order to prove that this is also 1, we will ideally want to find some other x prime y prime such that AB minus Ln x prime plus n times y prime is equal to 1. So, but how can we find these? All we have to do is just expand these and distribute over. So what we will get is AB times x prime minus L and x prime plus n y prime. Now we just take the n up front here, and what we get is times n times y prime minus l times x prime. Now, by just setting, now notice what we have. This is a, we call this y tilde and this x tilde. This is just an expression of the form ab times something plus n times something. Now, by selecting this x tilde, which is actually x prime, so let's just say, by selecting this x tilde, which is equal to x prime, being equal to x, where x is this old integer that we have here that we know that combined with a y in this linear combination will yield a 1. So by setting this x tilde equal to x, and by setting this y tilde, which is equal to y prime minus l x prime, which is just x in this case, we want to set it equal to y, so we will have that y prime is equal to y plus l times x. By having these two values set up, we will get that ab minus ln times x prime plus ny prime is actually equal to 1. So in other words, the GCD of ab minus ln with n is 1. And so we have proven that multiplication modulo n, in this case, is closed. And so we have proven this first property. So now for associativity, we won't prove it, but it's pretty easy to see why multiplication modulo n is associative. So we'll just check it like this. And so for the identity element, we just noticed that, well, 1 is in u of n, because for all n, the GCD of 1 with n is 1. So 1, and of course, so 1 is an element of u of n. And lastly, for the inverse element, let's prove that for any element inside u of n, there is an element that we will call a to the minus 1 in the same set, of course, such that we will have the following. So for each element, we can find its inverse. So let's see. So we know that for sure when we have an element inside u of n, then it will be relatively prime with respect to n. So the GCD of a and n will be 1. But by Bezout's identity, we know that there exists x and y in the integers such that ax plus ny is equal to 1. Or in other words, we have that n times y is equal to, actually n times minus y is equal to ax minus 1. But this just means that n divides ax minus 1. That means that ax is congruent to 1 mod n. So we found our inverse, it is x. And so with this we have concluded our proof that un is a group. So we now have that un with multiplication mod n is a group. And is it only a group? No, actually it also is a commutative group. So u of n is an abelian group of finite order. And of what order? Of order phi n, where phi is the Euler torsion function. So with this we have concluded our proof. Now let's look at some examples of multiplicative groups modulo n. So let's look maybe at u of 8. So let's see. So u of 8 will have 1, 3, then 5, and then 7 inside. And these are all the 4 elements of the group. So its order is 4. Now let's find the inverse of each. Actually, let's build a Cayley table for it. So now 1 times 1 will be 1, 1 times 3 will be 3, 1 times 5, of course, mod 8 will be 5, and 1 times 7 will be 7 mod 8, and this is the same for this column. Now let's look at 3 times 3. 3 times 3 mod 8 is 1. So 3 is its own inverse. Then 3 times 5 mod 8 is nothing but minus 1. So it is 7. Then we have that 3 times 7 is 21. So 3 times 7 is congruent to 21 mod 8, which is congruent to 5 mod 8. So this is 5. Then we have 5 times 3, which is congruent to 15 mod 8, which is congruent to 7 mod 8, so this is 7. Then we have 5 squared, which is 25, which will be congruent to 1 mod 8, so this is 1. So 5 is again its own inverse. And then we have 5 times 7, which is basically 35, will be congruent to 3 mod 8. So this will be equal to 3. So let us now fill the last row, which is 7 times 3. It will be 21, but 21 is congruent to 5 mod 8, so this is 5. Then 7 times 5, it is 35, which is congruent to 3 mod 8. And then lastly, 7 times 7, which is 49, is congruent to 1 mod 8, because, well, it's 48 plus 1. And so this is our Cayley table for U of 8. So now, as an exercise, you can try to the first thing which you can ask yourself is, well, what happens, well, this is pretty easy to understand what happens when n is prime, and then fill in a Cayley table, fill in the Cayley table for U7. And then as the second one, try filling the Cayley table for U15. And so these are two exercises that will help you build confidence with these sort of groups. So now let's move to another important example. So let's denote example number 3. And this time we're working again with matrices. So this example in particular is known as the general linear group. So first of all, we call GL of 2R the group of 2 by 2 matrices A, B, C, D, and of course with real entries, where its determinant, so the determinant of said matrix, which in this case is just AD minus BC, is not equal to 0. So we claim that this group here, with respect to matrix multiplication, is a group. So sorry, this set here, with respect to this operation, is a group. So let's prove it. So as a first property, actually, the first property that we would want to prove is associativity. So let's now prove it. So we need 3 matrices. So first let's multiply 2 matrices together, A, B, C, D, A prime, B prime, C prime, D prime, and then A tilde, B tilde, C tilde, D tilde. So let's multiply these two inside first. So remembering the row by column, like multiplication rule for matrices, what we will do is, well, the first entry for this product matrix here will be A times A prime, and then we will have plus B times C prime. Then here we will have A times B prime plus, well, B times D prime. Now we will move to the second row, and that is C. We'll have C times A prime plus D times C prime, and then C times B prime plus D times D prime, and then times A tilde, B tilde, C tilde, D tilde. Now multiplying all of this again will give, well, A times A prime plus B C prime all times A tilde plus, well, C tilde times A B prime plus B D prime. So this will be for the first entry. For the second entry, we will have A prime plus B C prime all times B tilde plus A B prime plus B D prime D tilde. So this is the second entry. The third entry will be C A prime plus D C prime all times A tilde plus C B prime plus D D prime C tilde. And here then C A prime plus D C prime B tilde plus C B prime plus D D prime D tilde. And so this is the end result. Now let's compute, let's keep this in mind, and let's compute A, B, C, D, and then inside parentheses A prime, B prime, C prime, D prime, and A tilde, B tilde, C tilde, D tilde. So, what we'll give is, in this case, A prime, A tilde, plus B prime, C tilde. Then on the second entry, A prime, B tilde, plus B prime, D tilde. Then C prime, A tilde, plus D prime, C tilde. And then we will have C prime, B tilde, plus D prime, D tilde. So this will be the result. And then multiplying again these two matrices, what we get is A times A prime, A tilde, plus B prime, C tilde, plus B times C prime, A tilde, plus D prime, C tilde. Then again, A times A prime. Well, actually, let's skip the calculations and then I'll just show the end result so that it's quick. So now, once we have computed this product, all we want to do is now show that each entry is equal by the definition of matrix equality. So let's check for the first one. So the first one, expanding it all out, is A prime, A tilde, plus B, C prime, A tilde, plus C tilde, A, B prime, plus C tilde, B, D prime. And let's expand all this out. A prime, A tilde, plus A, B prime, C tilde, plus B, C prime, A tilde, plus B, D prime, C tilde. And let's see. So this one is equal. This one is equal. And yes, it is equal. So we have obtained that the first entry is equal. Now let's look. Now you can quickly check that also the other ones are equal. I won't do that because we will waste quite a lot of time. So we will just put here that we checked that associativity actually holds. So now for the second property, we want to find an identity. But an identity here will just be the following matrix: 1, 0, 0, 1. And you probably remember this from, well, the linear algebra courses. To quickly verify why is that, just multiply this and see that, well, this will be A times 1 plus B times 0, so this is just 1, then A times 0 plus B times 1, B, then in the same way C, D. And also if you multiply it on the left, this will be true, so you will get the same matrix back. So we will call this matrix sometimes I 2 by 2, so the 2 by 2 multiplicative identity. So we will also verify that there is an identity. So now, the last property that we have to verify is that of an inverse element. And many of you might remember an expression for an inverse of a 2 by 2 matrices, for a 2 by 2 matrix, and you will remember that if you have a matrix that is A given by A, B, C, D, then its inverse, that we would denote by A to the minus 1, is given by 1 over the determinant of A times the following matrix, which is basically the first diagonal switched and the second diagonal negated, so multiplied by minus 1. And well, I leave it as an exercise to check that this is actually an inverse. And secondly, we notice that for each element in our GL2R set, there is actually such an inverse because we have that our determinant is non-zero. Now, for the last thing that we have to check is that, well, it's closed, but closure again is justified by a theorem in linear algebra, where we have that the determinant of a product of matrices will be given by the product of the determinants, and this assures that, well, if we have this, that this is not equal to 0 and this is not equal to 0, by the algebraic properties of, well, the real multiplication, in particular the fact that it has no zero divisors, we will have that also the determinant of AB will, and so we will have that this is also closed. And as a consequence of all of this, we will have that the GL, the real general linear group of 2 by 2 matrices, under matrix multiplication is a group. However, notice that it is not an abelian group. In fact, in general, matrix multiplication is not commutative, and I'll leave it also as this in an exercise to check. So check that this group is not commutative. You can just pick a counterexample to commutativity, and it's pretty simple to find. So now, as a last example for this video, we will look at another matrix group, which is known as the special linear group. And we will look at this group more in depth and prove some things about it when we will talk about subgroups for a reason. And what is a special linear group? A special linear group, in this case, we will also focus on 2x2 real matrices. Is basically the set of all 2x2 real matrices. So A, B, C, D are real numbers, of course, such that the determinant of such matrix is 1. So now, to prove that this is a group, and we want to show that this, we claim that this set under matrix multiplication is a group. So now, we don't really have to check again associativity, because we already did. And it restricts, of course, to the subset of the GL2R, because notice that this is, of course, a subset of GL2R. We don't have to check for identity, because we know that the identity is in SL2R, because it's determinant, which we can easily compute by well, the first diagonal minus the product of the entries of the first diagonal minus the product of the entries of the second one is just 1. So we have the identity, we have associativity, we have the identity. The only thing that's left us to prove is that, well, there are inverses, and as well as it is closed. So for the closure, again, we will use the theorem from linear algebra that we used above, that the determinant of a product of matrices is given by the products of the determinants. But if determinant of A is 1 and this is also 1, we will have that determinant of AB will be 1. And for another theorem will guarantee that there are inverses, because if we take the inverse of a matrix, then the determinant of an inverse of a matrix will just be 1 over its determinant. And so we will have that for each A in SL2R, A minus 1 will be in SL2R. So we have that SL2R under matrix multiplication is indeed a group. And we have proven our claim. So with this said, we have now covered quite a lot of examples of the structure of a group. So in the next video, I think we are ready to introduce some more abstract results about groups in general, and maybe give some more definition. So with this said, I see you hopefully all in the next video.